All right, so we have what's called a qualitative analysis scheme that helps us distinguish between a mixture of different ions, mostly transition metal ions here. So not exclusively, but a lot of them are, right? So let's say that we have a mixture of ions. So this is our mixture of ions. And what this problem, I think the best way to go through this or to understand this is just to go through an example problem here. So what we have is a solution that contains some or all of the ions listed below. And our job is to look at the experimental description and then classify these ions as being present, absent, or inconclusive. We can't tell. Okay. So to make our lives easier, I'm gonna like draw them again up here. So Sn plus 4, K plus 1. Barium, lithium, aluminum, and lead 2. Okay, so we're going to read this experimental description, and then we're going to try to determine whether or not these ions are present or absent in our solution. Okay, and how this is going to go is we're going to add a reagent, and we're going to observe any sort of change that occurs. Each reagent will selectively precipitate out a group of ions, right? So for example, I'm going to add 6 molar hydrochloric acid. If in my experiment I see a precipitate, that means that my solution contained either silver, mercury, or lead. Okay, so let's go to our experiment results. Whoa, let's go to our experimental results here. All right, this says that after the addition of 6 molar HCl, a solid is indeed precipitated, right? So we do observe a solid precipitate. So that means that we can conclude that it contains either silver, mercury, or lead. If we look in our mixture, one of our possibilities was this lead ion. So that, based on those results, we can conclude that our lead is indeed present in this mixture. Okay, let's do another one. Now we're going to go to the next step in our qual scheme here, and we're going to add this H2S in 0.2 molar hydrochloric acid. If we saw a precipitate, that would mean that our solution contains one of these ions on this list, you know, copper, bismuth, cadmium, lead, mercury, AS, I don't know what the heck that is, astenine, I think, antimony, and tin. All right. But if we look at our experiment here, it says that after this addition, no reaction occurs. So what can we conclude? We don't see a precipitate. That means that our solution definitely does not contain one of those ions there. And since tin was on that list, we know that tin is going to be absent from this mixture because we didn't say any precipitate. Okay. So for the next one, we're just going to keep on going down the line here, right? So now we go to our addition of this ammonium sulfide, and we observe a solid precipitate. So that means that we have one of these other ions present. And so let's use our eye clickers here. We're going to say, you guys are going to tell me whether it's potassium, barium, lithium, or aluminum, A, B, C, or D. Which one is present based on the results of this experiment? The fact that we have a precipitate of these group 3 ions. All right, I'll give you another 20 seconds here. Put in your guess. Let's see what we got. All right, so it's going to be the aluminum that we can determine is present. So again, we saw precipitation at this step here. That precipitate must be one of the following. It must be either aluminum hydroxide, iron precipitated out, chromium, zinc, nickel, cobalt, or manganese. That's how I can determine that it is aluminum that must be present based on the results of that experiment. Okay. So now we're going to move on. All right, now we have addition of this guy here. What is that? Ammonium biphosphate? I don't know. Anyways, produced no reaction. So my group 4, I did not get any precipitate. So what can I determine about my barium? It must be absent. Otherwise, I would have seen a precipitate at that step there, because that's one of my products that I would get. All right, and then the last one, the last set is these remaining ions that are soluble in everything. You can't precipitate out sodium, lithium, potassium, or ammonium. They just don't precipitate with anything. So how do we distinguish these group 5 elements? We go over and we do a flame test. And based on the color of that flame, we can determine what our element is. Lithium burns red, sodium burns yellow, and potassium burns purple. So we go and do our flame test. It turns out that our flame is purple. So that allows us to conclude that it is potassium that's present. And since it wasn't red, we know that lithium is absent. All right, so this is what's called a qualitative analysis scheme or a qual scheme. And this is where you're gonna basically, you just have to be able to utilize this chart here. This chart is what will be given to you, this whole thing. You have to be able to utilize that along with a set of experimental results to determine whether a set of ions are present, absent, or you can't tell based on the results of the experiment. Okay, so we worked through that first problem of this worksheet. There's another one here for you all to do on your own to make sure that you actually understand this particular part. All right, so that is this sort of, again, this qualitative analysis scheme, this qual scheme that would let us determine what ions we have in a mixture of ions. Okay, and what we're going to study about these transition metals, we're going to spend a lot of time talking about these transition metals and these coordination complexes that they form. Okay, come on. Trying to copy this problem over. There we go. What? All right. I don't know why it's not letting me resize it. So we're just going to work with it here. Okay. So what this is saying is that cobalt reacts with ammonia to form a coordination complex where the cobalt is now bound to 6 ammonium ions. And this is something that we're going to see a lot with our transition metals. They form these coordination complexes where they bind with what are called ligands. Okay. And this is going to be a big focus of this particular chapter. We're going to learn properties of them, how to name them, all that good stuff. For right now, we're going to focus on how to quantitatively determine how much of a complex is formed. Okay. So in order to do that, we need to start basically where we've started every single problem that we've done up until now. We need a balanced chemical equation. Where we have our cobalt ion reacting with this ammonia to produce this coordination complex, the cobalt with 6 ammonias bound to it. So everybody take a second and whoops, I forgot my charge. So everybody take a second and balance this chemical equation. How are we going to balance this? All right, hopefully you can see that in order to balance this out, I'm going to need to put a 6 there. Jaden, I see your question. Let me circle back to that at the end here. All right, so here I have my balanced chemical equation. I'm going to need this before I can do any math, right? We got to start with our balanced chemical equation. The next thing we're going to do is build our equilibrium expression. All right, so what do we remember for our equilibrium expression? Products over reactants. So this is my cobalt and ammonia complex. That's my product over my reactants. And remember, in my balanced chemical equation, these coefficients become exponents. Okay, so if we look at the Kf of this value, the equilibrium constant, what's called, it's got the F because it's called a formation constant, is given. This is 2.3 times 10 to the 33. Okay, so looking at this expression here, does this expression favor our reactants or our products? We're going to say A is reactants and B is products. So let's use our clickers. Which does this equilibrium favor? The products of this formation reaction or the reactants? All right, so this number right here, 10 to the 33, this is an absolutely huge number, right? That is 2.23 with then, 31 zeros at the end of it. That's an absolutely massive number, okay? And if I look at my expression, the only way that I'm going to get a big number like that is if this is big and this is small. So a large equilibrium constant favors the products, okay? Not only does it favor the products, it very strongly favors the products because this number here is just so big, right? And so these reactions here, rather than having to treat them as equilibrium expressions, right? We only really have to deal with equilibrium expressions when we have that dynamic equilibrium. This is a reaction that goes basically completely to completion. You have almost no of your reactants left over because of that large Kf. We're going to say 100% of that substrate gets, of those reactants, sorry, biochemistry terminology, of those reactants get converted into products. Oops, be able to do that. Okay, so we'll just make a note. Or what's called Kf. Whoa. Kf is so large we assume reaction goes 100% to completion. Okay. So that actually makes our lives a little bit easier in terms of determining how much product is formed, because I don't have to use the complicated algebra of an equilibrium expression. I can just use stoichiometry, right? Basic sort of stoichiometry to determine how much product is formed. Let's try this again. There it is. Okay. Cool. So now I'm going to take my balanced chemical equation and we're going to do some stoichiometry. So in theory, this is something that we should all remember from the first semester, but let's just sort of remind ourselves. We have in our balanced chemical equation, we are given a volume and a concentration of our cobalt ions. So we're given an initial amount of cobalt, and we're given an initial volume and concentration of our ammonia as well. Anytime you're given a finite amount of each reactant, you're going to have to perform a limiting reactant calculation. And this is going to be two calculations in one, basically. You're going to have to do two calculations in parallel with one another. First, going from moles of cobalt to moles of our complex. And then a second calculation going from moles of ammonia to moles of our complex. All right, so I'm going to do this first one with y'all, and then I'm going to set you free on the second one here. Make sure that we understand how to do this. So how do I get to moles? So I'm given, if we're going to start with the amount of cobalt, I'm given a concentration and a volume. How do I get to moles? Hopefully at this point, y'all have understood that we played this game over and over and over again. Volume times molarity equals moles. Okay, so that's exactly what I'm going to do. And what you're going to see how I set it up, I'm going to set it up in such a way that I'm paying very special attention to my units, because that's really how I know that I've set it up correctly. I know it's very tempting to get lazy and not write your units in there, but it makes it much easier to see that you've set it up correctly, as well as when you're looking back in your notes, you actually understand what the heck you were calculating, right? That's a big problem with just throwing numbers on the page, is you go back and you look at it and you're like, I have no idea what I did here. So making sure to annotate with units can help us a lot. So I got 4.3 liters of my solution times that concentration, where 1 liter is the 2.30 times 10 to the negative 5th moles of that cobalt. All right, so this here, this is my molarity. I just separated it into moles over liters so that I can see that my units are going to cancel out nicely. So if I stopped right there, I'd have more moles cobalt. That's not what we want, right? I'm trying to get to moles of my complex. And how do we jump from one side of our balanced chemical equation to another? For that, we're going to use the mole ratio that we get from our balanced chemical equation, right? Our balanced chemical equation is telling me that for every 1 mole of cobalt that's consumed, cobalt-3 ion that's consumed, I get 1 mole of my cobalt and ammonia complex. Okay, so if I look at my units, I can see that liters cancel out. Moles of cobalt ions cancel out, and I'm left with moles of my complex, which is what I want. So that's how I know when I'm being good about my units that everything is set up correctly. So then I can just punch it into my calculator, and I get 9.89 times 10 to the negative 5th. And if I'm being good about sig figs, that volume has limited me to 2 sig figs. All right, and units, again, I'm left with moles of my cobalt complex. All right, so everybody let's do, we don't have a ton of time in this particular class. So let's take, 4 minutes. Give me the moles of complex that we get starting out with our ammonia in this reaction. All right, so again, I'm going to start out with my volume times my concentration. I'll have to convert my milliliters to liters and my millimoles to millimolar to molar, because I have to have my units the same at the end of this problem. If I wanted to do the previous step in millimoles or something else, micromoles, whatever you wanted to do, that's fine. You just have to match it with the second one. So the fact that I did this calculation in moles, I'm going to have to keep it in moles down here. Otherwise, I'm not going to be able to compare those values. Okay. And this step right here, and well, so first of all, my units, right, work out where liters cancel, moles of ammonia cancel. So I'm left with my moles of complex. So that's important. Okay. This step right here, that mole ratio is really important, right? Because even though I start out, if you can prove this to yourself with the calculation. If I started out with, even though I start out with more moles of ammonia than I do moles of cobalt, in my reaction, 6 times more ammonia is consumed than cobalt. So I really have to account for that mole ratio in order to determine my limiting reactant. And so how do I figure out my limiting reactant? Well, I got to the end of these two calculations here, all right, starting with moles of cobalt and then starting with moles of ammonia. And I'm going to compare those two values. Whichever one is less, that's my limiting reactant. So in this case, I can determine that ammonia is limiting. Right? I have enough cobalt to make 9.9 times 10 to the negative 5 moles, but I only have enough ammonia to make 2.1 times 10 to the negative 5. So that means that in terms of actual moles of my complex produced, That's going to be that 2.1 times 10 to the negative 5. Okay, so I'll just actually update that up here. So 2.1 times 10 to the negative 5 moles of cobalt. All right. And again, we had to do our balanced chemical equation and then this limiting reactant calculation, which is actually two calculations in one. First, going from moles of cobalt to moles of complex, and then starting with moles of ammonia and getting to moles of complex. Okay. From those two calculations, I can determine that NH3 is limiting because that calculation gave me the smaller number. And so that's how many moles are actually produced. All right, so hopefully a little bit of review here of limiting reactant problems. So now how many moles of cobalt remain in solution? How are we going to do B? Okay. Just going to get rid of my markings here so I have some room. In order to figure out how much cobalt remains in solution, I got to figure out how much was actually used in the reaction. So in order to do that, I have to start with my limiting reactant and go to moles of cobalt. All right, so my limiting reactant is the one that gets all consumed. So that's what I'm going to start with. That's what I know is going to be used up in this reaction. I know how much cobalt I start with, but I don't know how much is actually used in the reaction because it's not limiting. Some of it's left over. So again, I'm going to start this the same way I started my previous calculation with the amount of ammonia that I have. Jaden, I imagine that it was when you converted from millimoles to molar or from milliliters to liters. So if we go 0.0070 liters, that's what I do when I convert from milliliters to liters. And my 0.018 moles of ammonia over 1 liter. And now, instead of using that mole ratio that jumps from one side of the chemical reaction to the other, I'm going to just stay on this side and jump from moles of ammonia, 6 moles of ammonia to 1 mole of cobalt. And this will tell me how much cobalt was actually consumed in the reaction. Okay. It's actually the same as the amount of the complex that was produced because they're 1-to-1. And importantly, what we just calculated is the amount of cobalt consumed. So if I want to figure out the amount that remains, I need to take my initial minus the consumed. That will give me how much remains. All right, so that initial amount was that 4.3 liters times the concentration, the 2.30 times 10 to the negative 5. It's 9.89 times 10 to the negative 5. And now from that, I'm going to subtract the amount that was consumed. All right, so I'm going to take my 9, whoops. And that's how I get my 7.8 times 10 to the negative 5 moles of cobalt remain. All right, so this is really, honestly, this is 100% review of stoichiometry that you would have learned in the first semester. I understand that it's been a while, but this is what we want to know how to do in order to calculate the amount of complex that's formed. These are called limiting reactant problems. So you want to flip back in your notes from the first semester in order to sort of remind yourself of what you studied about limiting reactant problems here. Okay, and the reason why we're able to treat this as a limiting reactant problem instead of an equilibrium problem is, again, just because this value for Kf is just absurdly high. So we're able to sort of assume or approximate that this reaction goes 100% to completion. It's not strictly true. There's always a little bit of dynamic equilibrium going on, or I wouldn't even say dynamic in this case. There's a little bit of reactant that's left over always, but with a Kf value that big, it's going to be insanely small, to the point where if we did account for it, we could always do our ice table or equilibrium problem. We would see that it wasn't worth our time. It was much easier to just treat it as a limiting reactant problem. All right, so now we're going to sort of continue on with this idea of these transition metal complexes, right? So we sort of talked about how cobalt, we're going to continue to use this as an example. So cobalt combines with 6 ammonias to produce this complex here, and we'll learn how to name this next class. But for right now, let's not get too bogged down in the sciencey words. Okay. So what we see here is that this, why in the world would these ammonias combine with this cation here, this cobalt ion, right? So we have our cobalt ion, and it's got a positive charge. Metals like to form ions that have positive charges. They easily give up their electrons, okay? And so what that means is that they're left relatively electron deficient. Because of that positive charge, they will attract electrons, like the electrons from the lone pair on the nitrogen in ammonia. Right, so these ammonia lone pairs, and we got 6 different ones that we can have. So cobalt's sitting there floating around in solution, and nitrogen or ammonia is passing by, and these nitrogen lone pairs are all going to be attracted to that positively charged cobalt ion. Okay, so it's because those transition metals like to form ions with positive charges that they can then bind to these compounds that have either lone pairs or maybe even a negative charge. We're going to see some of these ligands are actually charged themselves, but always negatively charged, right? Because they're donating electrons, and these are accepting the ions, the transition metal ions are accepting those electrons. All right, and we had special terms for these that we went over. Things that accept electrons are Lewis acids. Things that donate electrons are Lewis bases. And quite frankly, I absolutely hate that terminology because it's so misleading. When we think about acid-base chemistry, we're really talking about proton donors and proton acceptors. This is sort of an extension of that, but that is the sort of correct terminology. The other term that you'll hear, which I prefer, is Lewis acids are also called electrophiles, and Lewis bases are also called nucleophiles. Okay, but in essence, this is just a positively charged ion being attracted to negatively charged electrons. Okay, and the fact that it can accept 6 of these has to do with the electron configuration of it. These transition metals can accept up to 6 ligands. Doesn't have to be 6, it can be fewer, but they can accept 6 max. Okay, and in order to sort of understand that, it has to do with these electron configurations. We have to sort of remind ourselves about these electron configuration. So today is actually sort of a lot of review of things we probably haven't thought about in a while from first semester. Right, so for electron configurations, by that I mean that the electron configuration for example, lithium is 1s2, 2s1. Hopefully you guys remember this 1s, 2s, 2p business going on here, right? So what we need to be able to do is determine the electron configuration for these. First, let's just start with cobalt all by itself. Okay. And in order to do this, we're going to look at our periodic table. Ignore all that. That was for a different class. Okay. So in order to do electron configuration, we're going to spy where that element is on the periodic table, right? So here's cobalt. And the periodic table, we can divide up into these regions here. So this first 2 rows we call the S block. Okay. And I'm going to leave a space here for helium, because even though it lives over here, in terms of its electron configuration, we can put it there. This is what we call the P block. This is what we call the D block. And finally, this, you don't really use too much, but this is the F block. All right. So based on where an element lives, we know that it's going to end its electron configuration in that particular, with that particular set of orbitals. Okay. So sort of to annotate this periodic table further, this first row here, I'm going to sort of just white it out to make some room for myself. These are the 1s elements. The next row down, these are the 2s elements. Whoa, that's too big. These are the 3s elements, 4s, 5s, 6s. Okay, when we go to our P block, we can number it the same way. The only trick is that instead of starting at 1, you're going to start at 2. So this first row in the P block, these are the 2p elements. And then from there, it's just like it was before. You're just going to go down. So 3p, 4p, 5p, 6p. All right, and then our D block, we can do the same way, except for instead of starting at 1 or 2, we're going to start at 3. So these are the 3D elements. And then if we need to, we can do our F block as well. Although we're not going to really see these too much. They tend to sort of be a pain in the butt. There are a few like exceptions. But this would start at the 4F. All right. So when we say that we're going to do the electron configuration for cobalt, this will help us figure out what that electron configuration is. Importantly, it's going to end with this 3D orbital because that's what row cobalt is in. And the number of electrons in that 3D orbital is 1, 2, 3, 4, 5, 6, 7, because cobalt is the 7th element in that D block. So 3D7. Importantly, that isn't the whole electron configuration. That's just that last orbital that gets filled. Every element contains not only that outermost orbital, but everything that came before it. Whoa, bummer. Everything that came before it. So what do I mean by that? I mean that I got my 3D7, right? But I'm also going to have to include this 4s orbital. And it's completely filled. So that's 4s2. I got to go back to the one before that, which is the 3p orbital. And that 3p orbital is completely filled with 6 electrons. Before that was the 3s orbital. That 3s orbital has 2 electrons. Before that was the 2p orbital. That's filled with 6 electrons. Before that was 2s. And then finally, my 1s that's full, right? So this is the electron configuration for cobalt. You got to find where it is on the periodic table and then work backwards from there. Okay. So just for the sake of practice here, making sure we all understand what the heck is going on. Again, should be review, but just in case, I want you to tell me the electron configuration for molybdenum. Okay, take, let's do a few minutes here. Well, we only got 4 minutes, so that's perfect. Take 4 minutes to figure out the electron configuration for molybdenum and enter it into our iClicker here.
Does that say MO?
Yeah, MO, molybdenum. So this one right here
Thank
that I
you.
uncovered. Molybdenum. Yeah, cool. All for the noble gas abbreviation. Just remember that if you're going to use that abbreviation, you have to use the noble gas that came before it. So in this case, it would have to be krypton that you use for your noble gas abbreviation. We're not doing ions at this point, so just the neutral molybdenum ion. Although if it did form an ion, it would always be positively charged. Metals will never form negative ions. No, sorry, I see what the confusion is. This is just like a dash separating what will be my electron configuration, my 1s2, 2s2 business. All right, so again, based on where molybdenum is, I know it's going to end in the 4D4 configuration here. And then I just got to fill in everything that came before it. So 1s, 2s, then next is 2p, then 3s, then 3p, then 4s. I'm going to run out of room. Oops. And after the 4s is the 3d. And when it's all full, it has 10. 4p6, 5s2, and then finally I get my 4d4. And it's absolutely, I saw people using that noble gas abbreviation. That's great, saves us some writing, right? I can recognize that this right here, 1s2, 2s2, 2p6, all the way to 4p6, that is just the electron configuration of krypton. So we can use the nearest noble gas to abbreviate. So this would be the same as 5s2, 4d4, right? Both of those are the electron configuration for molybdenum. One's just represented in this shorthand for this noble gas abbreviation. Okay, so where we'll pick up with next time is looking at the noble gas, or rather the electron configuration of the ions that are formed when we make our transition metal ions, right? Which electrons in this configuration here are going to be lost?